On the Horizon. Editor, Osami Saijari. Saijari at cyberdefenseagency.com. Hey, our science fiction, quantum cryptography systems are now operational, with prototypes protecting internet traffic across metropolitan areas. These systems are so novel that we can consider quantum cryptography, or more properly, quantum key distribution, QKD, as the third and final insight to transform cryptography in the 20th century. In the 1940s, Claude Shannon provided the information theoretic basis for secrecy. The amount of uncertainty that can be introduced into an encoded message can't be greater than that of the cryptographic key used to encode it. To achieve perfect secrecy, the key must be at least as long as the message and never reused. That is, we must use Vernam ciphers, 3, also known as one-time pads. Unfortunately, in practice, it is difficult to distribute completely secret, completely random, one-time pads needed for Vernam ciphers, so they haven't been widely adopted. In the early 1970s, or possibly earlier, several researchers, including Whitfield Diffie, Martin Hellman, Ralph Merkle, Ron Rivest, Adi Shamir, Leonard Adelman, James Ellis, Clifford Cox, and Malcolm Optic, techniques are ubiquitous. Probably the most well-known are the Diffie-Hellman key exchange and RSA, prime factor algorithms. Unlike Shannon, who assumed that adversaries had unlimited mathematical prowess, public key techniques assume that certain mathematical functions are one way, easy to do in one direction, but too difficult for an adversary to undo in a reasonable time. For example, the RSA algorithm assumes that it is simple to multiply two large prime numbers to get their product, but quite hard to factor that product into the two original primes. However, no one has proved these assumptions. Invented by Charles Bennett and Giles Brassard in 1984, QKD begins with a radically different premise. We should base security on known physical laws rather than on mathematical complexities. Physical devices with specialized cryptographic protocols can conjure up ever-flowing streams of random bits whose values will remain unknown to third parties. When we use these bits as key material for Vernam ciphers, we can achieve Shannon's ideal of perfect secrecy, cheaply and easily. In theoretic secrecy, firmly based on the laws of physics. How does it work? QKD lets two parties, for example, Alice and Bob, agree on secret keys. More formally, it's a technique for agreeing on a shared random bit sequence within two distinct devices, with a very low probability that other eavesdroppers will be able to make successful inferences as to those bits' values. We use the random bit sequences as secret keys for encoding and decoding messages between the two devices. Thus, QKD is not in itself a full crypto system. Rather, we should compare it to other key distribution techniques, such as trusted couriers, the Diffie-Hellman key exchange, and so on. QKD can be an intensely confusing field. There are many approaches, the schemes are complex, and it helps to have a working knowledge of quantum optics, which is fundamental to the technology. I recommend Nicholas Gisson's article for a detailed review. However, the basic idea is simple, as Figure 1 illustrates. Alice sends a series of single photons to Bob, each modulated with a random basis, here a two-sided card, and a random value. Alice chooses a card side at random, writes a random 0 or 1 on that side, and sends the card to Bob. Bob also chooses a side at random and reads that side's value. When Alice and Bob choose the same side, Bob reads exactly what Alice wrote. Otherwise, he reads a 0 or 1 completely at random. After Bob reads all the photons, Chip Elliott, BBN Technologies. Einstein wrote, "I cannot believe that God plays dice with the cosmos, 1. But quantum mechanics has proved him wrong, and a remarkable crop of new cryptographic systems takes full advantage of those dice that Einstein found so troubling." Though most people think, on the horizon, which ones were correct? Then, Alice and Bob discard all values where they disagreed on the basis and keep the remaining values for raw key material. Now, what about an eavesdropper, who we shall call Eve? At first, Eve is in a situation similar to Bob's. She must guess which side of the card to read. Half the time, she will be able to read what Alice sent, and the other half she'll get a random value. But she can't surreptitiously siphon off a little bit of a single photon, because when she reads it, she demolishes it. But if Bob doesn't get that photon, it's no loss. The sifting process will discard that photon, and Alice and Bob won't use that bit in their key material. A clever Eve might try to regenerate a demolished photon and send a copy to Bob, but she can't. Quantum physics' no-cloning theorem says that she can't copy values from both sides of the card, only from the side she read. The other side will have a random value. If that's a side that Alice and Bob agree on during sifting, any Eve-generated random values will appear as small noise. Alice and Bob interpret all noise evidence of active eavesdropping. In a perfect world, that would end the story. However, in real system, some channel noise is always present, and a cryptographic system must operate with some noise levels, even they imply eavesdropping activities. To address this, we employ relatively elaborate error detection and correction protocols to find and correct bit errors and privacy amplify the result, so that Eve has a vanishingly small knowledge of the resultant bit value Alice and Bob use. Operating on bits in computer memory, privacy amplification is a classical algorithm that smears out the value of each initial shared bit across the shorter resulting set of bits. That is, it distributes its value via a universal hash across the resulting bits. Current systems. Bennett and Broussard built the first primitive QKD apparatus in 1992, 8 years after their first paper. Several systems followed since then, including systems built by Los Alamos, British Telecom, Johns Hopkins University, and IBM Almaden Research Center. Most were component parts, typically only optics. In the past year, 2 fully operational systems emerged from Los Alamos and BBN, 7-8, and 2 companies, ID Quantique, www.idquantique.com, and Magic Technologies, www.magictech.com, announced commercial systems but haven't provided public demonstrations. QKD can work through telecommunications fiber or through the atmosphere. Although these systems differ greatly in their technical details, researchers have demonstrated both approaches. Today's systems generate very high-grade key material at rates approaching 5,000 bits per second at distances of up to 50 kilometers through telecom fiber or 10 to 20 kilometers through atmosphere. While Figure 2, BBN Quantum Cryptography System, Anna and Boris, a fully featured quantum cryptography system now operating in the world's first quantum cryptographic network under the streets of Cambridge, Massachusetts. Alice, Bob. Photons. 1, 1, 0, 0, 1. Eve. Figure 1. The basic idea of quantum cryptography. Alice sends a series of single photons to Bob, each modulated with a random basis. Bob demodulates them with a random basis. Any noise in Bob's detection is assumed to have been added by an eavesdropper, Eve, who guessed the basis wrong in her eavesdropping. Alice and Bob can use those bits where they randomly selected the same basis, provided that the detection noise is low. On the horizon. On the horizon, along with conventional cryptographic algorithms, for example, the Advanced Encryption Standard, AES. Fortunately, there is a relatively clear, though challenging, technology path toward much faster systems. Today's QKD systems are severely limited by the rates at which they can detect single photons. Exotic new detectors based on cryogenic superconductors might remove this limit, or perhaps even more conventional, indium-gallium arsenide detectors tailored to the single photon regime. As real-world implementation examples, I'll describe Anna and Boris, see Figure 2, 2 systems BBN Technologies, www.bbn.com, built as part of the DARPA Quantum Network Project, http quantum.bbn.com, which recently began to operate the world's first quantum cryptographic network under the streets of Cambridge. Operational in October 2003, replacing our first-generation system, which started continuous operation in December 2002. These systems continuously generate key material and then use it to protect Internet traffic. We extended Standard Internet Protocol Security (IPsec) protocols to support the rapid rekeying of conventional encryption algorithms. Each system uses a highly attenuated single-photon telecommunications laser operating at a standard wavelength 1550.12 nanometers with phase modulation via unbalanced Mach-Zehnder interferometers and thermoelectrically cooled avalanche photodetectors (APDs), which are capable of detecting single photons. We implemented most of the electronics using discrete components, such as pulse generators, though we could integrate all necessary at Harvard University and will shortly install Boris at Boston University. Alice and Bob remain at BBN. They are linked by the Cambridge Dark Fiber Network, optical telecommunications fiber without amplifiers or electronics. The longest fiber length between Boston University and BBN is about 22 kilometers. Figure 3 highlights the system's features. The transmitter at Alice sends data using 0.1 mean photon number laser pulses. Each pulse passes through a Mach-Zehnder interferometer, which randomly modulates it to one of 4 phases, encoding a basis and a value in that photon's self-interference. The receiver at Bob contains another Mach-Zehnder interferometer, randomly set to one of 2 phases to select the demodulation basis. The received single photons pass through Bob's interferometer to strike one of bright pulse framing and annunciation. Gate 1550.12 nanometers, QKD data laser, signal splitter, amp, DWDM, circulator, delay line, delay loop, 50-50 coupler, delay loop, link, fiber, QKD weak coherent pulse generation, electro-optical phase shifter, adjustable air gap delay, optical attenuator, polarizer, adjustable air gap delay, 1550.92 nanometers, sync laser, 50-50 coupler, pulse generator, signal splitter, sync, buffering, digital to analog converter, trigger, phi, Mach-Zehnder interferometer, receiver, Bob, transmitter, Alice, delay loop, Faraday mirrors, electro-optical phase shifter, 3-way splitters, 1550.92 nanometers, sync pulse receiver, gated detectors, gate, 3 pulse generators, 2 pulse thresholds, Mach-Zehnder interferometer, 1550.12 nanometers, QKD cooled APD, QKD, quantum key distribution, DWDM, dense wavelength division multiplexing, APD, avalanche photodetectors. Figure 3, functional decomposition of BBN quantum cryptography system. Alice produces single photons and phase modulates them via a Mach-Zehnder interferometer for transmission over standard telecommunications fiber to Bob. Bob demodulates them with an identical interferometer and detects the values that Alice transmitted with his thermoelectrically cooled and electrically gated detectors. On the horizon, power level multiplexed over the same fiber to send timing and framing information to Bob. QKD protocols. Although a detailed discussion of QKD protocols is beyond this article's scope, QKD systems contain a surprising amount of sophisticated software. While developing our systems, we observed that QKD optics is perhaps the easiest part. The electronics are more difficult than the optics, and for a practical functional system, the software is harder than the electronics. Figure 4 illustrates how QKD protocols might integrate into a Unix operating system to provide key management for traffic via standard IPsec protocols and algorithms. BBN's QKD protocol stack is written in C for portability to embedded real-time systems. David Pearson, Gregory Troxel, both at BBN Technologies, and I present a more detailed discussion of this implementation and how QKD interacts with IK and IPsec elsewhere. As I previously mentioned, once Alice and Bob agree on sifted bits, they must perform error correction to find and eliminate any bits damaged or compromised by Eve in transmission. For example, bits sent as a ones but received as zeros. There are many ways to perform error correction, but each has 2 important consequences. Is a small possibility that Alice and Bob believe that they share identical bit sets, but in fact they do not. error correction requires communications between Alice and Bob, and, inevitably, assuming that Eve can obtain plaintext versions of such public communications, the process of error correction reveals sifted get information to Eve. Thus, the error correction's essential results are that Alice and Bob will, with high probability, have identical copies of their local memories, identical copies of a set of error-corrected bits, and Eve will have some knowledge of these bits' values, which Alice and Bob must reduce through authentication. On the horizon, error-corrected bit values to an arbitrarily low fraction of the total number of bits. At its core, it occurs as a randomized algorithms in Alice and Bob and public communication between them regarding the results of these algorithms. Finally, authentication gives Alice and Bob reasonable assurance that they are communicating with each other. In most modern cryptographic systems, this function occurs as some kind of one-way function. For example, digital signatures implemented by public key techniques. In classic QKD literature, authentication relies on shared secret keys, such in universal hash functions. QKD networks. The DARPA quantum network consists of two transmitters, Alice and Anna, and two compatible receivers, Bob and Boris, with quantum channels directly interconnected using fiber via a 2x2 optical switch. Either transmitter can negotiate a mutual key with either receiver. The switch is optically passive, that is, it does not detect or amplify any photons passing through it, so it doesn't disturb the quantum state of the photons that encode key bits. When two QKD endpoints don't share a direct or switched channel, but there is a path between them over trusted relays, our networking protocols let them agree on a shared key by choosing a path through the network, creating a new random number, R, and essentially sending an R one-time pad encrypted across each link. We call this process key relay, and the resulting network a trusted network, because this scheme's chief characteristic is that the key's secrecy depends on the endpoints and intermediate nodes being trustworthy. The BBN key relay protocols have been operating continuously in protocols. Let Alice build up a reserve of shared key material with Anna via a trusted relay at Bob or Boris. Similarly, Bob and Boris continuously build up shared key material via trusted relays at Alice or Anna. What's next? QKD's next generation will be even stranger than today's because it will draw key material from pairs of entangled photons. In some ways, this is the most satisfying of all forms of QKD because it directly exploits the universe's underlying randomness and strangeness. Such cryptographic systems create and derive their keys from highly unusual Siamese twin or entangled photons. The entangled state contains no information on the individual particles. It only indicates that two particles will be in opposite states. The important property of an entangled pair is that as soon as a measurement on one particle projects it, say, onto H, a horizontal polarization, the state of the other one is determined to be V, vertical, and vice versa. How could a measurement on one of the particles instantaneously influence the state of the other particle, which can be arbitrarily far away? Einstein, among many other distinguished physicists, could simply not accept this spooky action at a distance. But this property of entangled states has been demonstrated by numerous experiments. 9. Dick Baumeister. One of these systems is taking shape in BBN's Cambridge laboratory. Other teams, such as those at Bristol and Vienna universities, are proposing even wilder space-based Einstein's space-based IOPS. Einstein's spooky action at a distance consideration provides the engineering core for the next generation of cryptographic systems. References. 1. A. Einstein, Sayings of the Week, London Observer, 5 April 1964. 2. C. E. Shannon, Communication Theory of Secrecy Systems, Bell System Technical J, Volume 28, Number 4, 1949, pages 656 to 715. 3. J. Vernam, Cipher Printing Telegraph Systems for Secret Wire and Radiotelegraphic Communications, J.AISE, Volume 45, 1926, pages 109 to 115. 4. C. Bennett and G. Brassard, Quantum Cryptography, Public Key Distribution and Coin Tossing, Proc. INTL Conf, Computers, Systems and Signal Processing, CS Press, 1984, pages 175 to 179. 5. N. Gisson, etc., Quantum Cryptography, Rev. Modern Physics, Volume 74, Number 1, 2002, pp. 145-195. 6. C. H. Bennett et al., Experimental Quantum Cryptography, J. Cryptology, Vol. 5, No. 1, 1992, pp. 3-28. 7. R. J. Hughes et al., Practical Free Space Quantum Key Distribution over 10 kilometers in daylight and at night, New J Physics, Vol 4, 2002, pp. 43.1-43.14. 8. C. Elliott, D. Pearson, and G. Troxel, Quantum Cryptography in Practice, Proc. ACM SIGCOM 2003, ACM Press, 2003, pp. 227-238. 9. D. Baumeister et al., Experimental Quantum Teleportation, Nature, Vol. 390, 1997, pp. 577-579. Chip Elliott is Principal Engineer for BBN Technologies. His research interests include quantum cryptography and mobile ad hoc networking. He has a BA in mathematics from Dartmouth College. He is a senior member of the IEE, a member of the American Association for the Advancement of Science, the ACM, and the American Institute of Aeronautics and National.